Hello and welcome to NPTEL MOOC on electromagnetic waves in guided and wireless media. This is module 9 and in this module we switch the domains of the transmission line discussion. So far we have been working with what is called as the phasor domain or the frequency domain, wherein we dealt with, we did not really talk much about the time aspect. We assumed that all the voltages and currents were just phasors, meaning that they were they all had the same sinusoidal functional dependence or time dependence. But in this module onwards we will look at time domain applications, and this set of behaviors, when we are looking at the time domain behavior, is very important in many classes of transmission line problems. While the frequency domain approach is quite popular and works very well in case of RF frequencies and RF circuit design, microwave system design and antennas for example, when you come to the time domain analysis, this is very important in any modern processors or some kind of a communicating elements where you are communicating pulses, let us say on a printed circuit board between two ICs, or it could be from one PCB to another PCB. So, where the lines essentially become transmission lines. So, in all these applications it is necessary for us to look at the time domain behavior of the transmission line. Okay. For the responses in time domain are going to be very different in the frequency domain response, but it will but this time domain behavior is essential in designing these interconnection systems, and also looking at situations where the interconnection instead of becoming just a wire becomes a transmission line and starts to distort all the pulses that are transmitting. Okay. So, this broad area I would call it as signal integrity, meaning that you are looking at how what is the integrity of the signals or the pulses which are propagating on the transmission line between any two communicating chips. Okay. It could be on chip interconnection as well. So, many VLSI systems will have connection from one transistor to another transistor, but as the frequency increases on the on chip, even those small wires essentially become parasitic transmission lines, I would say, and then they will start to distort and the voltages and currents, and that has to be understood in the time domain. So, this is a complementary behavior or rather complementary understanding of the transmission lines as in from the frequency domain analysis. Of course, you could technically use another domain called as Laplace domain to understand the time domain behavior, and that is in fact done at in some special cases, but we will not do that here because we are this is an introductory course and we do not want to go into too much of a depth in invoking these Laplace transforms. So, we will look at some simple time domain analysis that would be sufficient for us to get the flavor of this signal integrity, and then we will see what this signal integrity means later on itself. Okay. So, we start off with a transmission line which I am drawing. Now, previously I would give the transmission line in terms of its characteristic impedance Z0 and perhaps the phase velocity. I would not have given the phase velocity normally because that is really not that of an important criteria, but sometimes if the transmission line has a different dielectric constant, then you may give the phase velocity, which will only serve to fix the wavelength lambda. Okay. Here we are not interested in this lambda wavelength, but we still need to know what is the phase velocity for a slightly different reason, which I will tell you now. Okay. So, I will give Z0, I will give UP, and I will give you the length of the transmission line, right. So, pretty much kind of the same parameters as you would do in describing this in the frequency domain. You will have these terminating loads as well, but this time the terminating loads will not be complex, meaning that we are not exciting our transmission line with a sinusoidal signals, and therefore an inductor subjected to a sinusoidal signal source will actually look like omega L, that is j omega L, and a capacitor would look like 1 by j omega C, and therefore the overall impedance was turning out to be a complex number, right. But now we do not have this complex number thing because we want to keep our excitations not as a sinusoidal excitation, but a slightly different one. In general we would like to have a pulse as well. Okay. So, the load will be either resistor or it would be a combination of a resistor and a capacitor, or it could be a resistor in parallel with a capacitor, or any kind of a network which will be a lumped parameter network. Okay. For simplicity, we will start with only resistively terminated transmission lines, because the methods that we develop here can be applied, cannot be actually applied directly to the cases where there are reactances. We need to be little bit different there. So, instead of introducing this complex case of having reactive elements or capacitors or inductors into the load, we will start with the simplest case of resistively terminated transmission line. Okay. So, that is our basic problem setup. I still have not of course talked to you about how I am going to what quantities I am interested in, but I am just interested in this load, which I will still call as ZL, but please understand that this ZL is actually equal to RL for at least a few more modules, this module and probably the next 2 modules as well, okay, or probably until the next module. The excitation that we are going to give to the transmission line will again have some load, okay, which could be just a resistive load. In this case I will call this as ZS. Please note that I am not calling this as Zg, you could of course call it as Zg as well, does not really matter. I am calling this as Zs to indicate that these are source quantities, because this terminology is quite common in the signal integrity applications, okay, or in the time domain behavior applications. You normally do not write it as Zg, because Zg is usually reserved in that RF circuit literature. So, I have a source which could be a pulse source as well, which we will call as Vs, and then connected that Vs onto Z0. Okay. Now, why is this up and L important? Up denotes the phase velocity, but I really do not have a sinusoidal signal for the phase velocity. So, specifying this up here is really not a good idea. Okay. So, I am not going to specify this up. Instead, I will tell you that if I have a rising edge here launched on the transmission line, then that rising edge will be available at the output of the transmission line. Just before it goes to the load, it would be available at a length, or sorry, at a delay of Td, which is given by L by U. Okay. I will not call it as phase velocity, we will just simply call it as the velocity U. That would tell you what is the delay through the transmission. So, if I have a rising edge of the pulse, then that rising edge will not be available immediately at the load side or at the load end, but it would be available at a delay, after a delay of Td seconds, okay, and that delay is the one way propagation delay, which is given by the length of the transmission line divided by the velocity u. Okay. So, you do not need to really know what is the velocity u here, you can of course still use the same 1 by square root Lc for the lossless transmission line and then write that as the velocity, or alternatively if someone has already given you Td by doing this kind of a measurement, then you can simply use that value of Td. So, normally we give you Z0 and Td, we rarely give you the length and the velocity, but if it is given, then it is easy for you to find out what is Td from this relationship, and it is important to note what is Td. Okay. And all these things are coming simply by assuming the the time domain behavior of the voltages are actually given in the form of V of t minus Z by U, where V is basically the voltage that is propagating. Okay. So, if at all this load were to be moved all the way to infinity, then there will only be a positively travelling voltage, which would be a function given by t minus Z by U, and at any plane Z equal to L, this would simply indicate that the waveform is delayed by a certain time Td given by L by U. Okay. Now, we are not going to consider infinitely long transmission lines, we will consider finite length transmission lines. Okay. And what we are interested in this finite length transmission lines is waveform on the transmission line at the load or at the source or at any point along the transmission line. Okay. At the load you are definitely interested, because that voltage will is the one that would be delivered to the load, but you are also interested in the voltages that would normally come back. If at all there is a mismatch, then this load would come back, the wave would come back, voltages and currents both will come back, and by monitoring this voltage at the input end of the transmission line, you can tell a lot about the load itself as well as the line itself. Okay. So, monitoring the voltages that actually come back at the receiver side, sorry, at the source side, and using that information to infer characteristics of the load is called as function of a device called as time domain reflectometer. Okay. A time domain reflectometer is just like a radar, it sends out a pulse and then monitors any return pulse. Okay. The changes in the shape of the return pulse as well as the, which includes change in the amplitude as well as change in the or the distortion that would be induced would tell you a lot about what is the nature of the load ZL. Okay. So, we will look at some TDR basics later on, but before we can do so, or we need to know how the voltages are going to be changed by this kind of a connection. Okay. So, that is all, that is what we are interested in. So, the problem as of now that we are interested is that I have a resistively terminated transmission line of appropriate length L or equivalently a time delay of Td connected to the source Vs and Zs. Okay. For simplicity, let us assume that the source is of a step voltage, okay, meaning that there is essentially a switch here. Okay. There is essentially a switch here and this switch would be closed at some time origin which we will call as t equal to 0, connecting both the voltage and Zs onto the transmission line. Okay. So, that is what we actually have. Let us take the amplitude of this source voltage as say some capital Vs, okay, and if you are interested you can give this as Vs into u of t, indicating that this is a switch that would close at t equal to 0 and connects both the voltage source Vs with its internal resistance Zs onto the transmission line which is resistively terminated with ZL. Okay. This is what we have. We will also assume that there is no initial voltage on the transmission line. We say that the transmission line is uncharged initially. Okay, what happens? Well, just at t equal to 0 when you close, remember there is no line voltage, there is no voltage anything or there is no current on the transmission line. At t equal to 0 the switch just closes and then this Vs is connected, Zs is connected to the rest of the transmission line. Now, think about this for a minute. Will this source voltage, right, this step voltage see the load immediately or not? It will not see the load immediately because the voltage has to travel all the way to the load, right, and then if there is a mismatch, only then this load voltage is actually seeing, in fact the travelled voltage is seeing this load only after a delay of Td. And then when it actually starts to come back, because assuming normally that there will be some kind of a reflection, then any changes that should happen at the generator or the source side will happen after a 2 times propagation delay, which is 2 Td. So, the immediate reaction or the immediate equivalent circuit that the source Vs and its internal resistance Zs sees will simply be something like this. So, this is your DC voltage. So, we will call this as plus minus with an amplitude of Vs that we have connected. So, I have this Vs and I have this resistor, internal resistor Zs connected immediately to the transmission line, whose characteristic impedance Z0 will be the one that the source will see. So, this is the equivalent circuit that the source Vs Zs is going to see at t equal to 0. Okay. Now, what would be the voltage that would be launched onto the line right away at t equal to 0, which we will call as V1. Okay. V1 would correspond to the amplitude of the voltage that is actually launched on the transmission line at time t equal to 0 by the action of this switch being closed. And this V1 is now simply given by the voltage division formula, right, which is given by Vs times Z0 by Z0 plus Zs. In fact, this is the voltage that would be launched onto the transmission line at t equal to 0. Okay. While the source may be at Vs, usually the voltage that is launched on the line will be less than that Vs and it will be given by V1 to begin with, and this V1 is the step voltage that would start to propagate. So, this part of the voltage would reach the load after a distance or after a length of Td. So, at which point it begins load or it tries to go into the load. So, this delay of Td is the delay, the edge or the voltage here, the point which I have marked in the red would actually start reaching and then start flowing into the load. But at the point Td, that is at time t equal to Td, right, the equivalent circuit at the load would look something like this. You have V1 here, I have just indicated with a DC source because that is what we are using, and then you have a characteristic impedance Z0, and then you have a load impedance ZL. Okay. It is not exactly like this, I would, so I will call this as Z0, but it is not exactly like this, but there is a voltage and there is a characteristic impedance Z0, and then it sees the voltage ZL. Okay. When Z0 and ZL are not matched, which normally happens, then only the incident wave and the transmitted waves, voltage waves cannot exist. There has to be a reflected voltage as well. So, in fact, at t equal to Td, there will be a reflected voltage, and what would be the amplitude of that reflected voltage, which we will call as V2. Okay. V2, and we will give it a direction V2 minus. Similarly, we could give a direction V1 plus, indicating that this is the positive going voltage or the forward voltage, and this is the backward travelling voltage. So, V2 minus will be given by the load reflection coefficient gamma L times whatever the voltage that was launched or that was available at time t equal to Td at the load end, and that is given by V1 plus. So, V2 minus is gamma L V1 plus. So, what is gamma L? Gamma L is basically ZL minus Z0 divided by ZL plus Z0. This number can be positive or negative, and this would be a real number now, because we have assumed resistive termination as well as a lossless transmission line, which means its impedance is also, characteristic impedance also real. Okay. So, this amount of propagate back, okay, and reaches this source side or the source end at t equal to 2 Td. At t equal to 2 Td, you now have, you can simply think of the source as a load now, and that would generate another reflected voltage, which we will call as V3 plus, and V3 plus will be equal to gamma S or gamma G, does not matter which one you use, gamma S times V2 minus. Okay. So, this is what the reflected voltage V3 plus would be. Because gamma S is usually less than 1, gamma L is less than 1, the amplitude V3 plus is usually smaller than the incident voltage. In some special cases it would be larger, but we will see what the special case is later on. So, V3 plus, and then it travels, generates V4 minus, then V5 plus, and so on and so forth. It continues in this manner until you are tired of tracking these voltages. Okay. Now, this may seem slightly complicated way of solving and finding out the voltages, and moreover we have just been seeing the amplitudes of the voltages. We do not know the shape of the voltage that we are going to see finally at the load and finally at the source if you are using a TDR meter, and you can actually solve for the shape of the voltages along with the amplitudes in a correct manner by utilizing a tool called as space time diagram for the transmission line, or sometimes simply called as lattice diagram. Okay. I am going to look at this lattice diagram and show you how it can be applied for a simple transmission line. We will have to see more about lattice diagrams in the next module as well. To begin with, lattice diagram is simply a two-dimensional representation. Okay. The two lines that I have drawn, the vertical lines correspond to the source as well as the load ends of the problem. So, z equal to 0 is the source end and z equal to L is the load end. So, you can see that the coordinate systems have been slightly changed. So, I have z equal to 0 as the source, z equal to L as the load. So, this is the z axis which will tell you where the load is located, and this is the time axis. Usually you give the time in terms of time delays, because those are the intervals where something significant happens on this problem. So, you can write this as 1, 2, 3, 4, 5, 6. So, when I write this 1, 2, 3, 4, 5, 6, I am actually implying that I am looking at time instance Td, 2 Td and so on up to 6 Td. Okay. So, 2 Td will correspond to voltage going from the source to the load and then coming back, and so by 6 Td you have actually done 3 round trips, and usually this amount of calculation is sufficient for you to get an idea of what would be the voltage. Okay. Of course, on this side also you can write 1, 2, 3, 4, 5 and 6, and now you are ready to begin the lattice diagram. Now, well, quite not ready, because you also want to know what is gamma L. Gamma L will be given by ZL minus Z0 by ZL plus Z0. gamma s will be given by Zs minus Z0 by Zs plus Z0. Okay. And you need to know what is the equivalent circuit that you are going to get at t equal to 0. So, that would be Vs with Zs connected to a transmission line of characteristic impedance Z0. Therefore, V1 plus is given by Z0 by Z0 plus Zs times Vs as the voltage division formula would tell you. Okay. So, now you are ready to begin. So, at t equal to 0, you start off the voltage V1 plus that would be launched, and of course, at the source it simply continues, right. So, this would be Vs, it continues all the way to infinity, but this starting point of the voltage Vs, instead of Vs being completely available to the load, what you actually get is V1 plus, right. So, the first voltage V1 plus also start with an amplitude of V1 plus and continues forever to infinity, right, but this will not be available to the load at after a time Td. So, after a time Td, you will now see this voltage appearing at the load, okay, and this portion is actually kept. So, what if the load is now, instead of keeping at z equal to L, you keep it at z equal to L by 2, then the time delay would reduce from Td to Td by 2, right. So, you can actually capture this entire thing by drawing a straight line, okay, and marking the voltage value V1 plus starting from z equal to 0 source to z equal to L time, and when you do that, so these 2 points are marked because the voltage V1 plus will reach the load at t equal to Td. So, now it reaches here, but as we have seen, a voltage now coming through a transmission line of characteristic impedance Z0 terminated in Zs load, sorry, L load will actually see a reflected voltage of the amplitude V2 minus, which is given by gamma L V1 plus. You know V1 plus from this diagram, you know gamma L written directly below that one. So, you now start a V2 minus which would move in the direction from load to source. So, V2 minus is equal to V1 plus times gamma L. You can actually write this separately factored in this manner, so that your problem will be slightly simpler to solve, okay. All information are being properly given. So, you now have a V2 minus. So, what would be the total voltage that you would see at the end of t equal to Td on the load? You would actually see V1 plus V2 minus, which is actually V1 plus into 1 plus gamma L, and this 1 plus gamma L is called as the transmission coefficient, okay. So, at the end of t equal to Td, if you are actually looking at you put a oscilloscope at the load and you are looking at the voltage changes, you will see that the voltage suddenly changes at t equal to Td to a value that is given by V1 plus times tau, where tau L is equal to 1 plus gamma L. If you do not like tau L, you can simply write down what is the, calculate the voltage and just put the voltage value down there. And until the time 3 Td, nothing really happens on the load. Why? Because there is no voltage coming back, right. The partial voltage will come back at 3 Td, because V2 minus, which has now reached the source, will be reflected off and forms V3 plus, right, which will then be launched at t equal to 2 Td and then goes all the way towards the load at this point, where it would be reflected off to give you V4 minus. Therefore, at 3 Td, the voltage will jump from V1 plus tau L to V3 plus V4 minus plus whatever the earlier voltage that you had, that is V1 plus tau L. So, this would be the total voltage. So, it could be jumping down or it could be jumping up, depending on the signs of tau, depending on the signs of gamma L and gamma S. So, I will just assume that for this problem where I am not given you the numbers, I will simply assume that it has actually jumped by an amount, okay. And this continues up to 5 Td, at which point you will again see a jump. Perhaps this is, the jump will be smaller, and eventually after certain jumps you will reach a final value or the asymptotic value, which in fact would simply be given by. So, if you call this as V infinity, that V infinity is simply given by Zs Zl, okay, connected to Vs. That is the value that you are going to see. V infinity will simply be Zl by Zl plus Zs times Vs. This is also making sense because the line is lossless. So, eventually the total voltage that you are going to see on the load has to be equal to the case where there was no line, right. So, line is lost, it is not storing any energy, it is not dissipating any energy, I should say, right. But it does take its time when the conditions are not right, it does take its time to reach that asymptotic value, and that is where the transmission line is going to be, I mean the transmission line effect is actually being seen. If there was no transmission line effect, then the voltage would immediately jump as soon as the switch is connected, the voltage at the load would jump to the final value of V infinity, but now it will take many times t. So, maybe at least 4 or 6 TD times for it to actually change or be very close to the final value V infinity. Okay. So, this is the voltage that you would see on the load, and at the source what you would see is initially you would start seeing this Vs minus, but at 2 TD, because there will be a voltage V2 minus that comes in from reflected from the load, you will see a total voltage change of V2 minus plus V3 plus. So, this step change that you are going to see will be V2 minus plus V3 minus, why V3 plus. Why V3 plus? Because that would be the partial voltage that is reflected at the source. So, V2 minus then V3 plus, which is reflected, that would be the step voltage. And again, I am not really looking at the numbers correctly, we will do that number calculations in the next module, but this would be what you would actually try to see, right. So, you would again see that voltages are actually changing at the source as well as they are changing at the load. Okay. Not just that, sometimes you are interested in knowing what is the voltage at the midpoint of the load, let us say. So, at the midpoint, meaning at z equal to L by 2, you are going to wait until a length, I mean until a time delay of Td by 2, right, for the voltage to change, and at that point it changes to V1 plus, then you will wait until up to that 1 Td later. So, that would be say 1.5 Td. So, at 1.5 Td you will see that it would change a value from, so this is half Td, this is 3 Td by 2, where you will see a jump of V2 plus, this is V1 plus, and then similarly V3 plus and so on. Okay. Again I am showing all of them to be increasing, but in the next module we will actually put down the numbers and then consider some very special cases which are also very important to see what is the effect of this different types of loads, or rather different values of loads, and how they would affect the signal integrity. To give you a basic idea before we go, the idea here is that if I have a logic gate and another logic gate connected by a transmission line, then, and if I say that I need a certain voltage at the load IC for it to be considered to be a digital 0 or a digital 1. So, let us say digital 1. So, a digital 1 requires a certain threshold voltage V. In the case where there was no transmission line, any switch change or any sudden change at t equal to 0 because of the source IC changing would be immediately available to the load. There is no ambiguity whether the voltage that the load IC is seeing is actually less than threshold or greater than threshold, that would have been immediately available. However, now although the final voltage may be greater than the threshold voltage, because it takes sufficient time. So, let us say it took about 5 Td time of the voltages because of the non-desired but present transmission line, you would see that the voltage reaches its threshold voltage at 5 Td, right. So, if the receiver would wait or the receiver IC would wait until 5 time delay, then it would know that the actual voltage coming from the source IC is greater than the threshold and it has to be considered to be a logic 1, but that would either mean slowing down the devices so that you give sufficient time to account for the transmission line effects, or not to slow down and not to slow down the devices, but run it at regular speed and then incur lot of errors, right. So, that is where the signal integrity is going to hit you, it is going to give you lot of errors which otherwise would not have happened if the transmission line itself were not to be present. Thank you very much.